Hello, welcome back to CS422 Theory of Computation. We are talking about advanced computability theory. We are in the middle of chapter 2. And advanced means we're talking about some sophisticated concepts about program transformation in order to compare problems, their decidability and undecidability. And we have already made great progress in formalizing the concepts that we have been talking about so far, mostly intuitively, such as the notion of an algorithm was not really required to become too formal so far. But then we have decided to make it formal with the notion of a loop program and later a while program, because loop programs turned out to be not powerful enough, not rich enough to compute, for example, the diagonal Ackermann function. And now we're talking about other transformations on programs such as type conversion, which is the mathematical term in interpreting a function of two variables as a family of functions in one variable and vice versa. And for this, we have introduced some terminology, which I'd like to recall for your convenience. Maybe we use the angle brackets to denote the encoding of a while program as a natural number. And we use the inverse angle brackets to denote the decoding of a natural number into some program, while program. If this natural number C is not the code of a program or of a syntactically incorrect program, then we'll adopt some convention to say that this is the code of a trivial program, which just simply ends without even starting, or a program which never ends, which is executed indefinitely. It doesn't really matter for the purpose of our investigations in computability theory, because syntactical correctness is decidable and therefore can be checked in advance. And we can kind of convert program that is syntactically incorrect into a program that just terminates, or into a program that executes an infinite loop. These are the cases, the trivial cases that we're not considering, similarly to why we're not considering finite decision problems, because these are trivial anyway. And yeah, we talked about type conversion mathematically and the algorithmic version, saying there's an algorithm that converts a given algorithm that receives two arguments and given a fixed value for the first argument into an algorithm that only receives and acts upon the other argument. That's described here. And the converse is, so this is a Smn theorem after the initials of the computability theorists who have formulated it. And to be fair, when it was formulated historically, it referred to actually not to while programs, where it's more or less trivial, and all your programming experience also makes it trivial. But at that time, it was introduced and stated in terms of mu recursion, which is much more advanced. And then later, it was shown that mu recursion is equivalent to Turing machines, is equivalent to the while programs that we consider in this lecture for pedagogical reasons. So that's why the statement looks much more frightening than it actually is. And also its proof is pretty straightforward because, and that's the reason why we prefer to the while program approach in this course. So the converse to this type conversion, converting a bivariate program into a univariate program, is a little bit even more involved to state, but the intuition is kind of similar. Given a sequence of programs in one variable, this can be converted into one program that receives two arguments. That's this idea, and here is the formal statement. And finally, closer under composition, given two codes of two programs, one can convert that into a single code of one program that computes the composition of both. Again, this is simple, pretty obvious when stated in terms of while programs, but it is beneficial and kind of to state things abstractly independent of while programs in computability theory, because all the different approaches are equivalent anyway, so let's not refer to any specific one. Good, so that was our recap, and then we've started talking about Fixedpoint theorem in computability theory, and based on that we're going to prove the existence of Quines in while programs. And actually I gave you the kind of assignment last time to try to write a Quine in your favorite programming language, and this is our opportunity to have a brief quiz. So my question for you is, please paste the Quine in your favorite programming language that you have devised over the last weekend over Chuseok. A Quine being a program that outputs its own code, source code, without accessing hard disk or any other external medium. So let's take a short break here, stop here, and please post the Quine in your favorite programming language. If you have not, understandably, spent Chuseok writing code for CS422, then this is an opportunity to look up. The internet is full with Quines, but I want you to understand why the Quines that you will find in the internet in your favorite programming language to actually work and do what they purportedly do, namely output their source code. So please take 10 minutes of time, fix your favorite programming language, Python, Java, C, C++, and search the internet for Quine in this programming language, then study and understand how that works, and then paste the source code of the Quine here in the chat. 10 minutes break. Thank you. Oh, one important remark. Yes, for academic honesty, please, if it is not your own source code, then please give credit, say where you found the source code of the Quine, okay? You're welcome to search and use the internet. If you do, then please also paste the link or some other reference to where you found it. Thank you. And here we are back. Thank you very much. And now let's have a look at the Fixedpoint theorem, its proof, and how we can prove the existence of Quines based on the Fixedpoint theorem in a very abstract setting, namely for while programs. And the proof works, since all are equivalent, also for Turing machines, for mu recursive programs, for lambda calculus. It's a generic proof. That's one of the benefits of the abstract approach to computability theory, the axiomatic approach using, like, for example, the SMN and the UTM theorem without referring to a specific programming system. So Fixedpoint theorem, you know what a fixed point is mathematically. A fixed point of a function from the space to itself, to the same space, is a value where the function maps the value back to itself without changing it. So here we consider function from natural numbers to natural numbers. That means fixed point is a natural number that remains the same, that remains unchanged if we feed it, if we plug it into the function. And what we're going to look at is actually not actual mathematical fixed points, but semantic fixed points. Fixed points where the value f of x may actually be different from x and f of x may be different, but they must represent the same program. And that's a very subtle thing. And to make this more precise and formal, let's introduce the following equivalence relation on partial functions. We say two partial functions are equivalent if first they have the same domain, say partial functions, so they may be undefined somewhere. But if one function is undefined, then so must be the other function and vice versa. That's the first condition. And the second condition, if the function is defined, if there are some argument, then both functions must also have the same value. By the first condition, they have the same, they are both defined. And by the second condition, they must have the same value. That's a reasonable definition, and it's easy to check. Maybe this is a next quiz to verify that this is an equivalence relation, but this is too easy for you, right? So we're going to skip that. Why is it interesting? Because we can now formulate this equivalence relation on natural numbers in terms of actually equivalence of two programs. So here, remember this terminology. It means, here we are, it means this is a program with whose code is the natural number x. This is a program whose code is the natural number y. And these two programs are supposed to be equivalent, compute the same function, partial function in this sense, although the natural numbers themselves, x and y, may be different. You have experienced this many times. If you get a programming assignment, then most likely any two of you will write two different codes, but all of these codes will be equivalent in this sense that they compute the same functionality. And so now we introduce this equivalence relation on natural numbers based on the equivalence relation between programs, or rather between the functions computed by these programs. And so this is maybe a new relation on natural numbers from computability theory. And to further understand that relation, let us recall, for example, here an example. Here P is a program. The angle brackets mean encode that program into a natural number. And the other angle brackets mean decode it to recover the original program. And these two programs are now equal, not just equivalent, but they're really equal, meaning they have the same source code. Whereas if we change the order of the angle brackets, if we take a natural number, if we start with a natural number C, not with a program, and now we interpret this natural number as a program, this means these brackets, and then encode the program again that refers to these natural numbers, then this is going to be equivalent to the original natural number in this sense. Good. Right. And here's a maybe more advanced example, namely the semantic extension. So to this end, consider some partial function psi from natural numbers to natural numbers, psi a partial function. So for some value arguments y, it may be defined. For others, it may be undefined. And from this, we construct a new function psi prime, which turns out to be a total function. And that's why it's called an extension. So the original psi may be a partial function, and the new one will be a total function. Let's check how the new one is defined. So the new one is also receives argument y like the old one, and then considers the return value of this function psi of y. And let's for now suppose that it is defined. Okay, first case, suppose psi of y is defined, then this represents a natural number. The angle brackets mean consider the program that is represented by this natural number. This is a program. And now we can execute this program on the argument z, right? So we can program receives an argument, and here we consider the program represented by the natural number psi of y, and execute this program on argument z as a thought experiment. And now we let z vary, so that the new program receives z as argument, and y is here fixed, is hard-coded, so that this now represents a new program, the program that receives z as argument, and then execute the program, represented by this number, receives z as argument, and then it makes the following execution. And the final outer angle brackets mean consider the code of this program. Okay. And what I'd like to point out is that this new natural number, right? This new natural number has the same semantics. It's equivalent to the natural number returned by this program. So that's why it's called a semantic extension, right? So let's check that. So if this is defined, then what is the semantics of the program represented by this number? So if you put here angle bracket, then it means a program. What is the semantics? The semantics is precisely that semantics. Maybe this is a program that receives some argument z, and then runs on that argument z. This is what we've just written here in a very complicated way. And this is the code of this program. And this may be a different code than the code of this natural number, but they have the same semantics, that behave the same way. Both this natural number and the program it represents, and this program and encoded as a natural number, receive an argument z, and then execute this program whose code is psi of y on this argument. So these two, psi prime of y and psi of y, are equivalent in terms of, in this sense, they represent the same program if psi of y is defined. Now we're doing all this in order to also cover the case where psi of y is undefined, in case psi is a partial function. What happens then? Psi is a partial function, then maybe psi of y is undefined, right? Whereas if psi of y is undefined, then this expression is undefined, but following our convention, this undefined expression interpreted as a program means we interpret it as a trivial program, which either just stops immediately or which deliberately enters an infinite loop and never returns. The point is that even if psi of y is undefined, interpreting this undefined natural number as a program gives rise to a defined program, trivial, but a defined program. And we can run this defined program on argument z, so that this is indeed defined program even when psi of y is undefined. Psi prime of y is always defined, possibly trivially so, but it is defined. And the important part here is if psi is a computable function, where no algorithm is able to tell whether psi of y is defined or not, because that's a halting problem, right? Halting problem says, given psi and given y, whether psi on input y terminates, whether it's defined or not. This is a halting problem. We cannot algorithmically solve the halting problem, but this transformation into this program, this can be done computable, and thus results in a possibly different program which semantically agrees with this program, but this one is now a total program. So that's a very subtle and important and illustrative example of this advanced computability, equivalence, and semantic extension, turning a possibly partial computation into a total computation that always terminates and that agrees with the original one whenever the original one was defined. If the original was undefined, then this new will still be defined with some arbitrary value, and the conversion is computed. And we're going to use that in a minute, and thus you will see why I've been introducing this, because first now we want to state and then prove the fixed point theorem. Fixed point theorem says every total computable function from natural numbers to natural numbers has such a semantic fixed point, that is a natural number such that phi of x is not necessarily equal to x as natural number, but equivalent in the sense that both represent codes computing the same function. And notice that every single hypothesis and also the statement is kind of important and optimal. If we consider partial functions instead of total functions, then maybe a partial function cannot have empty domain at all, right? That's a worst case, in which case the statement becomes wrong, trivially so. Also, the statement trivially becomes wrong if we try to replace semantic fixed point with an exact fixed point, stating that this must be equal. This is wrong trivially. For example, consider the increment function phi, which is a total computable function, but it has no strict fixed point. But the statement says it still has a semantic fixed point. So there are many very interesting and subtleties hidden in this statement. And now we're going to look at the proof of this statement, which is, I'm going to say mind-boggling. That's the genius of it. It's a very ingenious and abstract proof. So please buckle up and focus. The nice thing about this proof is, again, you don't really need big math behind it, just plain thinking, like large parts of logic, but indeed very clear thinking in order to not get confused. So it's a constructive proof, actually, right? So if you think about other fixed point theorem in mathematics, like Peano, Brouwer's fixed point theorem, or Banach fixed point theorem. Maybe some of you also have heard of Kakutani fixed point theorem. Many of these are non-constructive. They suppose that there's no fixed point and then result in a contradiction, which basically means the proofs cannot be converted to an algorithm for computing the fixed point, because if the proof is by contradiction, that cannot be turned into an algorithm. But here, this is maybe you also know Plarsky fixed point theorem, which also has a constructive proof, by the way. Right, so here it's a constructive proof, and here I just state this is going to be the semantic fixed point. It looks so easy, but let's look precisely. It uses the function psi, which is defined here, and applies this to the code of this composition of two programs. The program psi, that again I'm going to explain in a minute, and after that followed by the execution of the total computable function, or the program representing that function here. So what you see here is the composition of two programs and the code, the natural number representing the composition of these two programs. And we feed this natural number into the computable function psi in order to receive as argument, as value, a natural number. And this is going to be our x. and then we'll verify that X is indeed a semantic fixed point. So this is a, yeah, surprisingly almost like a one-line proof, but there's a lot of ingenuity behind it. And to see that ingenuity, let us see what the composition of phi and psi actually means. And here, this is where the definition, smart definition of psi enters. Psi is a function or the program that receives the natural number argument y, then interprets this natural number as a program, that is what this inverse bracket means, and then executes this program on the same natural number argument y. You might recall that we had such a similar construction when we proved the undecidability of the halting problem, where also we would, as a thought experiment, execute a program on its own code, and in practice, this is what happens when installing the GNU C compiler from scratch. And that's the same what we do here again, but with a different purpose, with the constructive purpose, not in order to diagonalize against something, but in order to prove something constructively. So to summarize, this is a program that receives as argument natural number y, interprets y as a code of a program, reverse square angle brackets, and then runs this program on the same argument y again. Okay, and now one important point here is to notice that this may be a partial function, right? Remember that y as a natural number y may well not represent a program at all, and we're going to get to that point in 5 minutes. But first, let's just, for simplicity for now, suppose that y is just such that this is defined. Then what does that mean here? It means take the result of that computation, right? And feed it into phi, that function, computable function, to receive another natural number. And this composition is then constitutes a program which we encode, and then we execute psi on the code of that program. What does it mean? It means interpret this code as a program. That basically means undo the encoding here, right? So these angle brackets are the inverse of these. So what the psi of this argument will do is a kind of here's the decoding, here's the encoding, and here's the decoding. That means execute phi after psi on what? On the argument, on the code of phi after psi, which is a natural number. Does it make sense? It's yeah, as I said, it's easy to get confused here. So this X means, according to this definition, interpret this here as a program, which actually it is a program, namely the program phi after psi, and then execute that program phi after psi on which argument? On the code of phi after psi. Okay, and remember, keep that in mind. Let me say it again. This here means, this is a program which means execute phi after psi on the code of phi after psi, because here it means encode and here it means decode, so that this here evaluates to simply phi after psi, and this evaluates to the code of phi after psi. Okay, and now let's compare that with phi of x. What is phi of x? Phi of x is phi of this. What is phi of this? It means execute the program phi after psi on the code of phi after psi. Now, if you've listened carefully, this is exactly what I've just said for x. And I've said the same thing for phi of x. In both cases, the semantics of x and of phi of x's execute phi after psi on the code of phi after psi. So since in both cases I've set the same semantics, that means that the two are indeed equivalent. X is equivalent to phi of x. Okay, let's stop here for 2 minutes, and please raise your hand if you got confused, or write it in the chat if you've got confused. Okay, some of you admit to getting confused and others do not admit or indeed have understood it. So yes, I'm happy to explain again. It is quite subtle and confusing. So one question refers to the point here that these two are stated to be equivalent and not necessarily equal. And the reason is right, because, okay, it may be equal, but it may also be just equivalent. That's the point here, right? So take some natural number, for example, a natural number that represents a syntactically incorrect program. And this angle brackets mean interpret this as a program and then encode that syntactically incorrect program. And that could be encoded in a different way than the original one. The main point is that the two programs behave in the same way, namely they do nothing or nothing serious. Right. And now, let's look at this another time again. Yes, it's really very advanced and very sophisticated and smart. So what this means in words, let's say it in words. This means, according to this definition, where y is now replaced by this natural number, the code of phi after psi, so that psi of y means encode, decode, that means execute phi after psi, right? So this means encode, this means decode. So this means execute phi after psi on which argument? On the code of phi after psi. So this means execute phi after psi on the code of phi after psi. Now let's look at phi of x. What does phi of x mean here? Imagine here's a phi in front of this. So that means phi after x execute on a code of phi after x, after psi. Phi after psi executed on the code of phi after psi. And now you see I've twice said the very same sentence, once for explaining the semantics of x and once for explaining the semantics of phi of x. And that means both have the same semantics. Yeah, this, I guess this takes really some time to digest. It is mind-boggling. It is a conundrum, and take your time maybe at home to convince yourself that both represent the same functionality, the same semantics, but as also has been pointed out in the chat, there's still the problem, what if psi of y is undefined, right? So if it's defined, then this is all good. But if y, the code of psi, phi after psi is undefined for psi, which we have no idea of knowing, right? Of course, it's also abstract. What then? And this is now Right. So this is not equal. These are just equivalent, but this is only partially defined, the function psi here, right? So that means this is not yet necessarily always actual semantic fixed point. It could be undefined. How do we get around that? And this is where our previous deliberations on the semantic extension come in. Namely, we replace in the definition of X, in the constructive proof, constructing X, we replace psi with a total semantically equivalent extension. And that's what we've done before, right? So we replace psi here with psi prime, where psi prime is this. And now the same argument goes through again, but now we don't need to worry about whether it's defined or not. So this is the final proof after several revisions of the fixed point theorem. Highly sophisticated, but yeah, really it's a proof that fits into 2 lines on a slide. It admittedly takes a lot of time to really understand. So, and understanding is something better done at home than online. So of course, the video recording and the slides are all available online. Let's now move on from this proof to an application of this fixed point theorem. And the applications are the Quines that you kind of already found and constructed ad hoc in the initial quiz. So let's remember, what is a Quine? A Quine is a program that outputs its own code. And now we can, so in the quiz, code here would refer to source code, but now in the abstract setting, it really means a natural number. Remember, the code of a program is a natural number, and the program that outputs its own code, yeah, naively, this runs into the same problem that you may have run into when you try to do it in your favorite programming language with strings, that the string itself must also be output. And so fixed point theorem asserts that there is a Quine in the while programming language in a very abstract setting. We haven't really been specific about how this encoding works. For different encodings, of course, Quines look differently, but the gist is that the Quines exist regardless of how we encode it. And again, this is a constructive proof, by the way, right? This is a Quine is named after this famous logician, Willard Quine, yeah, to honor his contribution. And so here's the proof based now on the fixed point theorem. And actually, it's a much more stronger statement. Namely, it says not only can a program, every program, it is no loss of generality that a program knows its code, but also that yeah, every program, whatever it does, not just output, but also can do anything else with its own code. And the subtle thing here is, if you have written a program, then the Quines theorem says this program can be converted into an equivalent but different program, such that the new program does know and can do anything with its source code. For example, outputting its source code, as you demonstrated, but a more powerful, or generally, it can do anything else with its source code, like perform some transformation before outputting it, or simulating it, or whatever. So formally speaking, it means the following. Consider a while program with 2 arguments, where first is going to be the parameter, the code. So here we consider a program which receives a source code as argument, and it receives the main argument y. So imagine P to be the source code of A, but we make it general. Of course, that's a cheating, right? That's like writing a Quine that accesses the hard disk or some other external memory to recover its source code, right? That's cheating, and that's what we do here to begin with. So this program receives its own source code or some other source code as first argument, and then proceeds to process its second argument. And then we convert that into a program which behaves the same way, different program but equivalent, remember? Different program but equivalent, in the sense that the new program behaves the same way that the original program that knew and received its own source code, only that the new program does not receive its own source code and still behaves equivalently. And this new program is constructed by considering the fixed point of this function. Okay, the semantic fixed point according to the fixed point theory. So here's a function that receives as argument the source code of this algorithm or any other algorithm, and then considers this source code hard-coded into this algorithm, into this while program, so that the new program only receives and processes the second argument. Remember, this is the Smn theorem. This is type conversion. This can be done computably, and then encode the new program, right? So here's the given program. Here is the source code of that program, for now still given. Convert that into the source code encoding of the program which has this source code hard-coded, okay? Now, why is this a Quine, right? So again, it seems like we have cheated here. We've hard-coded the source code of the program A, but no, we haven't. We've hard-coded any given source code, not necessarily of A, to recover a new encoded program. And this is a total computable function. It's computable because of the Smn theorem, and it's total because one can computably hardcode any given source code P into this program as first argument to recover the encoding of some program. But according to the fixed point theorem, this program has a fixed point, this function, right? It's a total computable function. So it has a fixed point, which we're going to call capital P. So that means that, what does it mean, semantic fixed point? It means that phi of capital P behaves the same way as P. Okay. Now, how does phi of capital P behave? It behaves like this program that would receive some source code, and P being a fixed point means that it behaves the same way as if it had received its source code as input, but it hasn't. So that this means the fixed point here, this program is indeed a Quine. Yeah, again, this is very confusing, I admit, but ingenious, that's the thing. Really, just one application of a fixed point theorem asserts that every program in any reasonable programming language can be converted into a program that is equivalent, but that knows its own source code. Very powerful statement. So yes, fixed point theorem and Quine theorem are two highlights of advanced computability theory. And now if you have gone lost, now is the perfect chance to resume, because we're going to move on to the next slide, which is about Rice theorem. Rice theorem is again one of the highlights in advanced computability theory. And here's a embarrassing mistake in the animation of the slide. Please ignore that line for now. Maybe we're going to have a look again at decidable properties of programs in order to motivate Rice theorem. So some properties of programs are decidable. Others are undecidable, like the halting problem, whether a given program terminates or not. And Rice theorem clearly identifies the border, the boundary between which questions, which properties of programs are decidable and which are undecidable. So it's a generalization kind of the undecidability of the halting problem to really ask the question of, you can ask basically any question about correctness of programs to see whether this property is decidable or not. And the first thing we observe is that syntactical correctness, as we said repeatedly, is a decidable property of programs, right? So that property is a decidable one. Another property is whether the program's encoding is, let's say, at most 10,000 characters long in ASCII code or in binary, doesn't really matter. Again, this is decidable. Just look at the code of the program, how long it is. Right? Here's a very small modification of the previous problem, namely, given a program, does the program make at most 10,000 steps? Let's say on the empty input epsilon. Again, this is decidable. How is this decidable? Yeah, simply simulate the program for 1,000 steps. And if it has terminated within 1,000 steps, then the answer is yes. And otherwise, the answer is no. Here, the bound of 1,000, that's what makes the difference. That was difference between halting problem would have no bound at all. And here, with a bound, this is decidable. So again, decidable. Whereas the halting problem asks whether a given program terminates at all, let's say on the empty input, with no bound. And then suddenly the problem becomes undecidable. This is the halting problem, right? Equivalent to the halting problem. So, and another problem here, decision problem, is the following. Given a program, is the set semi-decided by the program empty or not? And here, finally, we use the formal definition of L of P. So in order to understand that last terminology, observe that any given program, any while program, may terminate on some input and may fail to terminate on other inputs. And recall that semi-deciding means terminating on the inputs that belong to the set and not terminating on the inputs that does not belong to set. So that means that every while program gives rise and describes a semi-decidable subset of natural numbers, namely the subset consisting of all the inputs where the program terminates and omitting all the inputs where the program does not terminate. So, and the question is whether this set semi-decided by the program is empty or not, or put differently, whether there exists an input on which the program P terminates or not. This is kind of a, this is the non-triviality problem, right? So this is a non-triviality problem. And we've discussed before that this is also equivalent, not equal, but equivalent to the halting problem, and therefore undecidable as well. So, and this is to all these things to motivate the question of figuring out which properties of programs, these are all properties of given programs, syntactical correctness, the length of the program, the number of steps it makes, whether it terminates, or whether the set it semi-decides is empty or not, are all properties of given program. Some of them are decidable and others are not. And the question is why and which ones? And as I said, the answer to this question is given by the famous Rice theorem, which actually was developed and gradually generalized by several people: Rice, Myhill, Shapiro. So let's first have a look at the formal statement of this famous theorem. One of the highlights, did I mention this is one of the highlights of advanced computability theory? So in order to make this extremely general statement, fix some proper subset of the power set of natural numbers. So that means S is a collection of subset of natural numbers, right? So 2 to the n means power set of natural numbers, the set of subsets, and a proper subset means S contains some subsets of natural numbers, but definitely not all. And recall that there are uncountably many such subsets of natural numbers, and S should consist of some of them, but must admit at least one. On the other hand, S must be non-empty. I forgot to mention that. S must be, oh no, we're going to get there in a minute. So this is a subset. So this is kind of a collection of decision problems. That's one way of looking at it. And it's supposed to be a non-trivial collection, not the entire set of all decision problems. And here's the hypothesis of the Rice theorem that says this collection of subsets of decision problems must be non-trivial, must contain at least one, no, that's the other way around, one problem that belongs to S and one problem that does not belong to S. Yeah, the terminology is not perfect, but it makes sense mathematically. It must contain at least one subset of natural numbers, and it must avoid at least one subset of natural numbers. And both subsets of natural numbers are required to be semi-decidable, recursively enumerable. Under these very weak hypotheses, the following decision problem about given programs is undecidable. Given a program, consider the set it semi-decides, as explained here. Does this set belong to the collection of decision problems or not? This is in turn a decision problem, right? Let's give this decision problem a name, because this is really higher order, right? We're talking about sets of subsets. And here, every set of subsets gives rise to a decision problem on programs, namely whether this the set X of semi-decided by this program belongs to S or not. And the statement says this is undecidable, and a very weak hypothesis, namely the only hypothesis is that the set collection must have at least one semi-decidable set and must miss at least one semi-decidable set. Without this hypothesis, again, everything becomes trivial. If this, for example, the entire power set, right? Then this question becomes trivial, because if S is the entire power set, then the answer here is always yes. And we can easily decide that without looking into details. And similarly, if S is the empty set, then again, this decision problem becomes trivial, namely the answer is always no without even looking at the program. But as soon as the collection of sets here is non-trivial, contains one and misses one semi-decidable set, then the statement of Rice theorem says this becomes undecidable. And this, if you recall, look at it, recovers all these cases. What I want you to demonstrate that this is a great exercise in understanding the statement of the Rice theorem, that the items D and E are actually covered here by this. So it's really a strong generalization. And in order to prove that, again, the proof is going to be very elegant, very abstract, and arguably also very confusing. So please stay focused for the last 10 minutes of today's lecture, namely the proof of the Rice theorem. So an intuitive understanding of Rice theorem is the statement that any non-trivial property of the set semi-decided by a given program is undecidable. And what I want to emphasize here is, first, it must be non-trivial. This is captured by this hypothesis that the set of subsets here must at least contain one and must at least miss another semi-decidable problem. Not just arbitrary, but semi-decidable. And the second thing to emphasize here is that it's about a property of a set semi-decided program, not any property of the program itself. Let me say that again. Rice theorem is about undecidability of not undecidability of properties of programs, but undecidability of properties of the set semi-decided by a given program. Why is it so subtle? Of course, remember that the non-trivial property of a program is decidable. For example, whether the program is syntactically correct, or the property whether the program has at most 1000 characters length. These are properties of a program. These are not properties of the set semi-decided by a program. What is the difference? The difference is if we proceed to a different program that is equivalent to the previous one. Let's say we proceed from a program whose length is at most 1000 characters to a program that behaves the same way, but has added some comments to make it larger, longer than 1000 characters. Then that means that the property of being at most 1000 characters long differs. Although the two programs are equivalent semantically, but this is a syntactic property having length at most 1000 characters. It's not invariant under modifying the program without changing its semantics. So it's a property of a syntactic property. It's a property of a source code. It's a property of a program, not a property of the set semi-decided by the program. Properties of the set semi-decided program means that if we modify the program so that it changes its source code but still remains equivalent, then the property should also not change. Must be invariant under syntactic modifications of the program that do not change the semantics of the program. And these properties, any non-trivial such property is undecidable. Syntactic properties of programs can be decidable. Semantic properties of programs, non-trivial semantic properties are undecidable. That's the intuition behind Rice theorem. And now, finally, yes, final 5 minutes, the proof. And the proof considers two cases. And the first, undecidability means, remember, for example, it cannot be both semi-decidable and its complement. And we're going to show in both cases, at least one of the two conditions fails. Either this decision problem fails to be semi-decidable, or its complement fails to be semi-decidable. Depending on which case we are in, and which case, I mean, depending on which case we logicians are in, not the algorithm. Okay, and the first case is, suppose that the empty set belongs to this set system here, right? Right, this is possible. And the second case will suppose that the empty set does not belong to the set system and thus cover all possible cases. In the first case, consider given program input P, as usually encoded as a natural number, and we're going to show how we can use in our hypothesis that it is decidable. We can convert that into decision procedure of the halting problem for the given program P, which we know is undecidable, therefore real to contradiction. So proof, indirect proof, suppose it is decidable in this case, result in a contradiction, namely in the statement that the halting problem is decidable by using a decision procedure for this. And so this is a proof by reduction, as we've seen before. Namely, we convert the given program P into another program Q with the following behavior. Q first performs, executes, simulates P, and in particular, if P doesn't terminate, then neither does Q. But if P does terminate, then after having done so, Q will move on to invoke the program that semi-decides L. Remember L, if this belongs to S, then L minus, this is, I've mixed up these two, then L minus does not belong to S. L minus is a subset of natural numbers which does not belong to S here. Okay, Now let's look at the behavior of this new program. So new program, if the given program belongs to H, if the given program terminates P, then the new program Q will behave in the same way as the procedure semi-deciding L minus, which means the new program semi-decides L minus, which means that the answer here is positive, right? So if the given argument P belongs to the halting problem, then the program semi-decides L minus, which does not belong to S, and otherwise it semi-decides the empty set, because if a given program does not terminate, then the new program Q will never get past this simulation and therefore semi-decide the empty set. Okay, recall that any program semi-decides one unique set. In the first case, it's an empty set. In the second case, it's a set L minus, which is a contradiction because we know that the halting problem cannot be decided, but here this transformation, if the set system S were decidable, then that would allow us to semi-decide the halting problem in the first case. Now in the second case, we simply modify the transformation here. Namely, we make Q first perform P as previously. If P does not terminate, then that still means Q semi-decides the empty set, which is now not in S. Whereas if P terminates, then we make Q after termination invoke the program semi-deciding the other subset L plus, which now we are in the case does belong to S. So again, by being able to distinguish whether Q semi-decides the empty set or L prime, that means one can also semi-decide decide whether the given program P terminates or not, which is the halting problem, and again a contradiction. So in both cases, if the empty set belongs to S, and if the empty set does not belong to S, in both cases, one arrives at a contradiction, at an algorithm, at a reduction for solving the halting problem contradiction. So this concludes our discussion of the famous Rice-Myhill-Shapiro theorem. And as time is running short, let me give you a cliffhanger of what we're going to do in the next and probably final lecture covering chapter 2, Advanced Computability. Namely, we will talk about Oracle while programs. We will introduce them, and I will then study the hierarchies of undecidability using the notion of reduction to compare undecidable problems. And just for reference, yes, we do not talk about Turing machines in this lecture for pedagogical reasons, but Oracle Turing machines are actually an invention of Alan Turing. I mean, Turing machines have been invented by Alan Turing machine when he was not even a PhD student, and then later he became a PhD student of Alonzo Church at the Institute of Advanced Study, and in his PhD thesis, Alan Turing introduced and studied Oracle Turing machines, as we nowadays call them. And in this lecture next week, we're going to study and introduce Oracle wild programs, which are the wild program equivalent to Oracle Turing machines without all the hassles of Turing machines. So that's all for today. Thank you very much for your attention, and see you on Thursday.